we are processing not still images, right, but 3D videos. So being able to efficiently process those videos is very important. For example, in the current challenges, we have a limited computation resource. So how to do this a large amount of computation with limited computation resource budget is very important. So today, G will give an introduction of the TSM, temporal shift module, and hopefully the driverless team can find some collaboration opportunity to use this technique to land it in your cars. Several companies has already been using this technology. For example, Baidu integrated this into their pedal framework. And recently, NVIDIA also had a forum and had a tutorial how to use the TSM on the NVIDIA forum. So lots of real world applications. Okay, with that introduction, let's welcome G to get started with the presentation.
Okay, thank you. Thanks, Professor Han, for the introduction. I will begin with sharing my screen here. Okay, can you guys see the slides?
Yes.
Okay, thank you. So, hi everyone, my name is Jilin, and today I'm very glad here to share my previous work on video understanding. So the title of my presentation is TSM, Temporal Shift Module for Efficient Video Understanding. So before we start, let's get into a little bit about the background. As we know that videos are growing explosively. So every day about 10 to the 5th order of hours of videos are uploaded to YouTube. So we need to process these videos for recommendations and potentially for advertisements. And also efficient video processing is essential for both cloud and edge. For example, in some cases like hospital, you do not want to upload your video to the cloud for processing. And also for our autonomous driving, we want to process the data locally on the car instead of transferring the data to the server. So such kinds of edge deployment requires a very efficient model to handle the streaming video data. So traditionally there are two ways to handle the video data. So video data is different from image data mainly because that there is one more dimension, that is the temporal dimension. And as you can see here is an example of 4 frames taken from a single video. So if you follow the different time arrow, you can give different prediction, like it's whether pushing from left to right or right to left. So there are 2 ways to process videos traditionally. One way is using 2D CNN at each frame, and after feature extraction, we calculate average or some kind of post-processing to give the prediction. So 2D based method is more efficient, but it cannot handle temporal related information because we actually do frame processing one by one. And the other way is to use a 3D convolution, which performs joint convolution along spatial and temporal dimension so that we can do some kind of spatial temporal modeling. But since there's one more dimension in the convolution, so 3D CNN are actually far more computationally expensive than 2D. So to deal with the dilemma, we hope to achieve 3D CNN performance in video modeling while we just use 2D CNN complexity. So this is why we propose what we call temporal shift module and also TSM. So there are 3 small figures down there. So we can first go to the figure 1. This is a tensor in a video understanding network. It typically composed of 5 dimensions, like the temporal dimension, which is number of timestamps, and the spatial dimension, which is the height and width, and also the channel dimension. So since we're here, we are discussing about the temporal information, so we do not need to focus on the spatial dimension. So in figure 1, we showed a feature map of 4 frames. So basically, this corresponds to applying a 2D CNN to each of the frames. So as you can see, in each row, we only have 1 color, which means you only have the information from this frame because you are just using a 2D CNN. And what we do is to shift parts of the channels along the temporal dimension bidirectionally, as we do in figure B. So after the shift, each row now has 3 colors, which means that we can effectively mingle the information from neighboring 3 frames together, so that we can perform some kind of temporal modeling. And we also have a so in Figure B, we shift the channels bidirectionally. We also have an online version for the video understanding. So online version means that you are doing video recognition from a streaming video, so potentially from a camera. So you only have the past frames and current frame. You do not have the future frames. So in such cases, you can only shift the channel along one single dimension. So TSM module is very simple by design, so it can be inserted into off-the-shelf 2D CN to enable temporal modeling. Since we only change the address of the data, so such kind of operation comes at the cost of 0 flops and 0 parameters. And this is how we use our proposed TSM module to design a video understanding network. So there are 2 versions of video understanding network, one for offline processing, which means you have all the video, and one for online processing. So for offline processing, the process is very simple. You just take a off-the-shelf 2D CNN network, and you sample multiple of frames from the input video, and you apply 2D convolution to each of the frames. So after each 2D convolution, you insert our bidirectional TSM module, which helps you to fuse the temporal information from neighboring frames, and it can be further fused by the next 2D convolution. So to perform online TSM, online video understanding, each time you actually just take one frame from the video input, from the camera input, and you give some kind of prediction. So what we do is to unroll the process. So basically, in the online version, each time we just shift out parts of the channels in the feature map as we did before, and we store them in the memory. So for the next frame, we just replace the corresponding channels with the feature from the last frame, and this is done in a repeated pattern. So for each frame, we shift out the feature and replace it with the information from the last frame. And is there any questions? I in the discussion, I'm not sure. I cannot open that.
Oh, do you add a temporal shift module after every 2D convolution?
Yeah, that's a good question. So actually, no. So here we show the example of adding the TSM module into a ResNet design, the ResNet kind of design. So here there's, in the upper image, you can see there's a residual connection. So what we do is to add one TSM module for each of the block, for each of the residual block. So it's like 10 each blocks for a ResNet. And we find out we can also reduce some of the TSM modules to, and it doesn't quite affect the performance.
I see.
Yeah, so anyone is welcome to just raise your hand and ask some questions if you have. And yeah, thank you. And so here we show that our TSM module is very easy to implement. For example, here is a PyTorch style code. It's just like 5 lines of code, and it's easy for the naive implementation. And we can show some results on such kind on some data sets. So before we introduce any further results, I would like to briefly introduce the data sets widely used in video understanding area. So for video understanding, so potentially, especially action recognition, the data sets could be roughly divided into two parts. So the first part is the less temporal related ones. So typical data sets have some classes like apply eye makeup or apply lipstick or doing some kinds of sports. So for these data sets, you can actually guess the what the people is doing just from one single frame. So it's not very related to temporal information. So on the other hand, there are some other data sets like something and gesture, like they are doing some kind of hand gesture recognition, a lot of temporal information to help you give the right prediction. So the first thing we want to show is that our TSM module can easily improve the performance over 2D baseline. So here we use a 2D baseline called TSM, which have a very similar name. But what I did is just to sample some frames from the video and apply 2D convolution, apply 2D CNN to give prediction and average the prediction for the whole video. So we insert our TSM module into the 2D baseline, and we find that we can improve the performance on different data sets consistently. So for less temporal related data sets, we can still slightly improve the accuracy by 3 to 8 points, while on more temporal related data sets, we can improve the accuracy by double digits. So all this improvement comes at the cost of zero computation and zero parameters. And our TSM module is also very efficient and it's also very accurate. So here we compare the performance of our TSM module compared to the 3D CNN we mentioned before. So here we use i3D, which is the standard 3D CNN that is the widely used. So another family is the ECO family, which is a previous state-of-the-art efficient video understanding method. So we compare the accuracy versus computation on a temporal related data set, something. So the area of the circle denotes the number of parameters. So we find that our model consumes about 3 times less computation than ECO family, 6 times less than i3D family, while achieving better performance. So on this data set, we are actually on the #1 place in the leaderboard when this paper came out. I think currently we are still very close to #1. And our model is not only have a smaller computation, it's also very friendly for hardware inference. So our model has higher hardware efficiency because we use 2D convolution, which is better optimized than 3D on existing hardware like GPUs. So here we show some simple comparison for latency tested on NVIDIA GPU. So each time we just feed one video to the network because we want to get a latency here. So compared to the 3D network, we can achieve 9 times speed up while still having about 2% higher accuracy on these data sets. So on other cases, we want to maximize our throughput for the system. So this is typical for offline video processing. For example, you want to process all the videos uploaded to YouTube. So here we use a batch size of 16 and measure the throughput. So our model has a 12.7 larger throughput, times larger throughput compared to 3D network, while achieving better performance. So all the above results are introduced for the offline video recognition. So for driving scenarios like autonomous driving, what we care about is more about online video processing. So imagine you are driving a car, you are like getting a streaming video from all kinds of cameras and you want to do online video recognition. So firstly, we compare that the online version of TSM and offline version of TSM. So do they have a difference in performance? So we measure this kind of benchmark on existing data sets. We find that actually for most of the video data sets, we can achieve the same level of accuracy just using online version of TSM. So online video processing can also give you a very good performance. So the other task we care about when doing online video recognition is how fast can we recognize an action when it emerges. So for example, you just imagine you are in a healthcare facility like a hospital. So you have some elderly patients and they tend to fall to the ground sometimes, and we have a video system to alarm you to when the people fell. So we hope the system can give a fast prediction by just seeing the very starting point of the action. So here is a early recognition result on a video action recognition data set. So compared to a previous method, where our model can achieve 90% accuracy while only observing the first 10% of the video frames. So so all the above results are on video classification. Like for example, we want to classify what the people is doing. So here we show some online video detection results, which is more related to the driving scenarios. So this is a video taken from, so before we start, I will introduce, there are two kinds of methods we compare. The left one is a 2D detection method. So basically it's a detection method applied to each frame separately. So we are using RFCN, which is the standard detector on these data sets. So on the right side, we plug our TSM module into the backbone of the RFCN detector. So here we compare the results of using or not using temporal information. So as you can see, for most of the times, both detectors give reasonable results. But when the car is facing you, there are some glares to the camera, so it can lead to some false positives. For example, the left one detects there are some kind of train. There are some kind of train in the box in here, which is clearly not reasonable because we are previously detecting this is a car. So for our TSM module, with the help of temporal information, we can easily get rid of such kind of silly mistakes. So we evaluate the detection system on ImageNet VID datasets, which is a video detection datasets. We also, besides the 2D baseline RFCN, we also compare to a state-of-the-art temporal-based detector called FGFA, which is a feature-guided, flow-guided feature aggregation. So it uses optical flow to fuse the information of, I think it's 15 frames from, so it's basically the current frame, the previous 7 frames, and the next seven frames. So it's not even a online method. And it also introduced a larger latency, about 2.5 times latency, while our method can outperform FGFA while without incurring any extra overhead compared to the 2D detection method. So we also find that our model works best for the fast moving and medium moving speed case. So this is because when the object is moving very fast, it's hard to detect by a single frame. But if you have the help of temporal information, we can trace back in time, which help us to detect the fast moving object. I think this is a very common case in driving, because sometimes the cars are driving very fast in your point of view. So our TSM module is very highly scalable, so it can be scaled up and scaled down. So we first talk about scaling down, like we show how we can scale down our TSM model to some kind of very edge devices, so we can achieve low latency and low power deployment. So here we show that we deploy our TSM module on these 5 edge devices, 2 Jetson devices, and also a Raspberry Pi and 2 smartphones. I think these 2 smartphones are not very state of the art now, but they are still, we can still achieve real-time inference. Like we are hitting 30 FPS here. And on the most left-hand side is the Jetson Nano board, which only costs about $99 to buy, and our model can run more than 70 FPS on its GPU, which is far more than real time. So on all these devices, we are consuming about 5 watts for the power, which is just similar to an LED light bulb. So on the other hand side, we can easily scale up our TSM model for training. We can do some kind of large-scale distributed training with submissible computer. So submissible computer is basically what my background is. So it's currently the best supercomputer in the world. So so different from training from ImageNet, training on some kind of large video data sets is even more resource consuming, because videos have many frames while image has only one frame. So so this kind of large data sets imposes a problem, like how many resources do we need for training? So typically, if you just train on a single machine, which could take days to finish. So instead, we scale up our model training to submit supercomputer using a lot of GPUs. So in this case, we are using about 1,536 GPUs for distributed training. So this allows us to speed up the overall training by 200 times. So we can shorten the training time from more than 2 days to just 14 minutes. And in this way, we can achieve and at the same time, we do not suffer from accuracy loss. So the original accuracy training on one node, one submit node consisting of 6 V100 GPU is 74.1%, while after scaling up, we still get the same accuracy here. Our model also achieved very good scalability. So in distributed training scenario, scalability means how many times can you speed up the training divided by how many times of more resources that you use. So ideally, we can achieve a linear scale up. For example, if you have 4 times more machines, you can scale up the training by 4 times. But in real world, different machines have to communicate. So there is a very large communication overhead, which stops you to achieve a decent scalability. So here we show that our scalability is actually very good. So even on like more than 2,000 GPUs, we still achieve about more than 85% of scalability. So we are using Submit supercomputer, which is a very good hardware. But on the other side, we also need a very good model to maximize the training throughput. So here we show our TSM module is more scalable than traditional F3D models. So compared to 3D models, we are about 2 times, we can have about 2 times higher training throughput. So this, which shows that our TSM module is hardware friendly for distributed training. So these 3 curves shows the ideal scalability, which is in dotted line of TSM actual scalability, and also the 2 lines for 3D networks. So finally, we have some results on dissecting TSM modules about the spatial-temporal feature it learns. So we now know that our TSM module can do some kind of spatial-temporal modeling, but how can we verify that? So what we do is to feed a video into our trained TSM network, and we try to find out what different channel is actually modeling. So here we feed some video samples and find the attention of each channel and circle it in the foreground. So there are some very interesting discovery. We find that even we are only training with classification labels. For example, one label could be move something away, and we did not give the detection label, which means we did not provide the region or the location where the action happens. But our model can automatically learn a spatial temporal action detector. So for these 3 videos, we find that the attention of channel 5, it precisely circles out the region where move something away action happens. And for the other channel, it precisely locates the wiping action. So in the video, also there are many frames. The action could happen only in a very small, only a very small fraction of frames. So here we also can precisely detect that. And here are some examples of discovering the action pushing to left. So we also compare our learned attention compared to the 2D network, which is also TSM. So here are some examples which shows that our model, with the help of temporal modeling, we can find the action detection location, while the region where action happens, while 2D network can only focus on the object. For example, in the first video, it basically circles out the box, but you don't know where the hitting is happening. So if you see closely in the first 4 frames, there is a pen hitting the box. And same for the next 2 video clips. So here is a demo of deploying our Gesture Nano to deploy our TSM model to a Gesture Nano device. So this is recorded before, so we are performing some kind of gesture recognition in real time on this just a nano device. And this kind of application could be very helpful. For example, when you're driving, you can like communicate with the computer in your car using your fingers. For example, you can control the map. And here is the demo modified on top of the action recognition, gesture recognition demo, where you can use your gesture to navigate through a Google map. So this is Josh. Sorry. So this is Josh, and also an intern in our lab. So he used this technique to develop such a demo. So you can navigate like in Street View, and also you can also navigate in like the map, like zoom in, zoom out, and move the location and sort of things. So, and also I recorded a demo on hitting like on the something data sets, which is kind of fun to look. So basically we are doing online inference on this video, and it figures out what I'm doing with the simple objects here. Yeah, so lastly, I would like to thank my advisor and co-authors on this work. And also we got a lot of help from IBM and Oak Ridge National Laboratory for the supercomputer for us to play with. And finally, there's one paper and also a short report related to the talk before, and we have released the code for our for the project, including the gesture recognition demo. So you are more than welcome to try it out.